energetic nuclear particles coming out. So I was been interested in a long while focusing on experiments to focus on the mechanism. So I don't want to do electrochemistry. I don't want to measure heat. I want to do experiments where I can measure what it is that's going on under the hood inside. So proposed phonon nuclear coupling as a mechanism that underlies what's going on. And we set up experiments to try to find it. And we had lots of years where we didn't see things, or we saw things and they weren't quite right. And these days we're doing excitation transfer experiments, which seems to show something working. The implication, if this is correct, is that excess heat and cold fusion Fleisch-Pons effect is a small part of something much bigger. And that's my interest. So I've been working on models for only 30 years. So we start with the phonon nuclear coupling, then we'll have a basic interaction. If we want to study that interaction, ideally you'd like to see a nuclear energy transit, a nuclear state make a transition and see a phonon come out. That would be a single phonon process, and we don't have phonons in the kilovolt region of the crystals. So we're left with the excitation transfer being the lowest order effect that we would have a chance of looking at. If we have many excitation transfers, and each transfer is one quantum, one phonon, then we can transfer a large amount of energy as long as we can keep the system coherent. So I've been interested in that. So to account for excess heat, we have subdivision and then down conversion. For just up conversion, the collimated X-ray radiation, I think, demonstrates that. All in all, we get from this kind of model toolbox that allows us to address many different anomalies. So the phonon-nuclear interaction, you might say, well, people have been thinking about phonons, thinking about nucleons, basically since the 1920s. How can there be anything new? Of course, there isn't anything new because Bright noticed that there was an interaction between the motion of a nucleus and the momentum and velocity back in 1937 when he did the first reduction of a relativistic nucleon problem to the non-relativistic version of the problem. And so he found a coupling, and he didn't like it because he said, well, if your nucleus is moving, if it moves at constant velocity, then you can just rotate out the coupling because it's just the same as this in the rest state, except you're moving. But on the other hand, if your nucleus moves back and forth, then it's, you can't pull the same trick. So from my perspective, Bright found it, he wanted to get rid of it, but in an accelerating frame or an oscillating frame, you have to keep it, and it gives rise to an interaction between what's causing the vibrations and the nuclear states. The effect's known in the literature for other applications. If you start from a relativistic Hamiltonian and you do a rotation, this is partial Fold-Equal-Twoson transformation. You get a term showing the nucleus kinetic energy as a particle. You get a relativistic description of the internal nuclear states, and then you get a coupling between the momentum of the nucleus and the internal degrees of freedom. If I expand it out, that A matrix looks like all this stuff. And the way to think about it, there's a simple way to think about it. If you imagine an atom with electrons that interact with one another, the magnetic interaction depends on the velocity. So if you take your atom and you move it, then the motion of the electrons is increased so that the magnetic force is increased if you're going this way and decreased if you're going this way. If you move back the other way, then it goes the other direction. So it's a boost correction, and it's expected. There's nothing magical about it. What's not been appreciated is that if a nucleus is moving in a lattice, relativistic effect, well, it's not moving very fast, but it's still there and it can cause some coupling. So for excitation transfer has been proposed since the late 1920s, around 1930. And one of the problems that appeared prominent in connection with this discussion is energy exchange in biomolecules, chlorophyll, that kind of thing. You can find a lot of papers in biophysics on excitation transfer these days. Our proposal is to move from electronic excitation transfer to nuclear excitation transfer. So in excitation transfer, the basic idea is you start with, say, an electron or nucleus that's excited, and another one, in this case, is the same, but it's not excited. And this one can be de-excited to go to this state where the excitation is flipped, or you can go this route. So excitation transfer is indirect. You have to go through intermediate states. And so some time ago I was trying to explain this to Florian, and so Florian was saying, okay, where's the energy come from to get you from here to here? And I'm trying to explain, well, no, the energy doesn't come from anywhere. It's a quantum coherent thing. It's a virtual state. This is a virtual state that they're coupled to, and the fact that you don't have enough energy to get there means that the dynamics is impacted. And this question comes up again and again and again, but the issue that getting from here to here via these states is a quantum mechanical effect, and there's no classical analog. So this state's off of resonance, this state's off of resonance, but this state is on resonance. And this notion of off resonance, on resonance is going to become really, really, really important in a few minutes. The question is if I have a nucleus and I want to push it off of resonance, how do I do it? Do I roll up my sleeves and push? No, I use an excitation transfer, and if I couple to this state, and the nuclei in this state, depending on the details, the technical details in fine print, but by coupling to this, I push the system off of resonance, or I push the system off of resonance, and that's going to have concrete implications for me. I stole a slide from Seymour Mu's thesis defense here to save time. He analyzed a very simple version of it and took the 6 levels and reduced it to a 2-level system. And by doing so, there's all kinds of cancellation, and we get a result here. So there's 2 or 3 things that are of interest here. To go from here to here, the contribution going this way cancels from the contribution going that way. So by the time that you get to the end of it, this indirect interaction is far weaker than the initial coupling that was present in the system. So the bane of my existence since I first started working with these kinds of things in the late 1990s was the destructive interference. So even though the coupling can be strong for an excitation transfer effect, the destructive interference whittles it down so by the time you're done there's hardly anything left. If you want it to work better for nuclear excitation transfer, you want a high photon energy, you want a low nuclear energy. Okay, let's think a little bit about applications that I'm going to come back to. I have some results which I think are really big and really important. One application proposed in the 1990s was excitation transfer as a way to account for low-level nuclear emission. So, for example, there were some early experiments by Chambers, by Lipson, by others, where they saw very energetic alphas over 10 MeV, 15 MeV, over 20 MeV. And I propose this in connection with that observation. If D2 goes to ELN4, you get 24 MeV. If this excitation gets transferred over to a plated nucleus, that gives you the energy to dig out an alpha or proton or neutron. And Lipson also observed very energetic protons, and Brzezinski and Boss, Lipson, and others have observed very energetic neutrons. So this mechanism has been proposed for as a way to understand these observations. we're hopefully going to be getting in an ion accelerator, and we're going to put this mechanism to the test, hopefully in the coming months, so we can, hopefully next time I talk to me, it's like, yes, we know for sure that this is how it works, or alternatively, we know that that was another dumb idea. Okay, good. Okay, so there's been a lot of interest in the Lipinski and Lipinski experiment. Basically, they brought in protons at around 500 volts or so, hit lithium metal target, and basically saw all kinds of things. The initial experiments were done with very energetic protons, and they saw more P lithium-6 products than they had expected to. It's P lithium-7 than they'd expected to. So their documentation is in 2 patent applications. I want to focus on one particular experimental series or experiment result. So they have a target chamber, vacuum chamber. They've got a proton gun coming in. They've got a piece of lithium here. They've got a screen to change the bias voltage. They've got charged particle detectors. Charged particle detectors. Okay, they're there. I don't see them. Front detector, here's one of them. Anyway, various diagnostics. The biggest signal that they saw in this experiment is this, and it's a very large number of protons. It's a little bit less than 500,000 counts per second. It's under 1 MeV, around 0.8 MeV. And from their point of view, these are backscattered protons. And I'm scratching my head and looking at the documentation. Protons coming in at 500 volts. How do you backscatter the best part of an MeV? One of these days I will figure it out. But at the moment, they're ignoring this. I'm looking at this as potentially the #1 signal that I'd like to see, that I'm interested in. And one of the reasons I'm interested in it, I said, well, suppose it were one of these excitation transfer things. So it's protons and some deuterons mixed in because it's isotopically pure protons. So maybe it's PD going down. And I said, let me have a computer code, idiot computer code, look through every single isotope that's stable. What kind of proton energy will come out? Well, it turns out there's only one that can occur that can get me protons at energies anywhere close to what's under discussion. In this case, I have a reaction, excitation transfer gets me lithium-6 going to P plus helium-5. That gives me a proton of 0.88 MeV, which is a little bit above the 0.78 MeV that Lipinski and Lipinski see it at. I'm thinking, well, if it's created a little bit into the lithium, it'll lose some energy coming out. So this is a candidate. And you can say, well, why don't I see alpha particles at a little bit higher energy? And my answer is, well, I don't know. Maybe the coupling is favored to a single proton than to a deuteron for internal nuclear reasons. In other words, I don't have a good idea, but it's still a candidate. Also, in the same experiment, after about 10 minutes or so of running, they get this peak out. So this peak's a little bit over 8 MeV. And they identify it as being the protons fusing with lithium-7. So the reaction energy is larger. You would get 8.6. So Lipinski are proposing this reaction is occurring in some new and interesting way, which would give you 8.67 MeV alpha. If you look at their data, their alpha signal is well above that. You get counts over 9 MeV. So I personally am not convinced. I tried calculating, so if you get all these protons out, maybe the energetic protons will give you P lithium-7. So I simulated and modeled it. What I find is that the secondary P lithium-7 number of alphas would be too low by a factor of 100 to explain their observations. So then I said, well, suppose that the injected alpha might be another one of these current excitation transfer things. So I said, let's look at D2 going to helium-4. This excitation transfer going to lithium-7 gets you here, and you get an alpha particle at 9.13 MeV. Moreover, if you say that the deuterium and hydrogen in the proton beam is natural, you end up with an inverse factor of 2, getting quantitatively the right amount, the right ratio of the low energy proton signal and the high energy alpha signal. So at the moment this looks really good. Like I say, we've got a proton gun on the way, and hopefully one of these days we'll see it and be able to untangle what's going on. Okay, talk about experiment. We were interested in doing excitation transfer experiments. The first proposal was for this unbelievably good idea, this LANR. We're going to provide the phonons by having an inverse transducer, which will vibrate the whole plate. We have cobalt-57. If we have excitation transfer to iron-57, if it happens to be in the plate, or the cobalt-57 decays inside the state of iron-57, if we can excitation transfer to ground state iron-57. If it was by megahertz vibrations, the whole steel plate would vibrate. We have other detectors looking at other parts of the steel plate. So we take an excitation here where the cobalt is, and have it come out someplace else, centimeters away. That would be a dramatic demonstration. So the experiment's done. That doesn't work at all. So my elegant, really good idea is broken. On the other hand, when Florian did the experiment, we got this. So if the half-life is 271 days, so we should have seen this. What we saw was this, and the way to think about it. So this is the 14.4 kV transition. So the cobalt decays initially in state at 136, which 80 plus percent, 85% of the time, as I recall, goes down to 14.4 kV state. And then we're looking at this transition from the 14.4. Now, after lots and lots of experiments, what I think is going on is this mesh is sort of giving us a pinhole window to look at part of the cobalt. And the part of the cobalt we happen to be looking at had more iron-57. So if you have excitation transfer, the excitation moves from where there's less iron-57 to where there's more iron-57. So in our view, the excitation moved to right behind the hole. And so at the beginning of the experiment, it went ahead and gave us more output. So if I were able to extend the experiment back, the emission would be low, 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 and goes up and then comes back down. And we've seen that in many other experiments, so we know that that's the kind of effect that happens. Over the each different color stripe here is a different day. So over the course of 11 days or so, the excitation goes down. The interpretation today is that Florian screwed the clamps onto the steel as a way for us to try to get loss for our very elegant version of the experiment. And probably what happens is that the wood stress reduces by creep with a time scale something like this. That's impacting the steel, the evaporated cobalt-57 and the epoxy, giving us some stress, making some terahertz phonons. And I think the terahertz phonons are making this excitation transfer happen. So the excitation is moving from the place where the 14.4 kV state is born, and it's probably moving in this particular experiment the best part of a millimeter. We'll talk more about that. Florian will talk about that in his presentation, and in future months and years we'll have more documentation of our talks once we sort more things out. Okay, we also have evidence for anisotropy, angular anisotropy for the harder gammas. Basic ideas for the harder gammas, the rate of decay is much faster. It's 8.7 nanoseconds instead of 98 nanoseconds. So basically, the 1 over delta E makes excitation transfer weaker. The shorter lifetime means you don't have a long time for coherence. So I think resonant excitation transfer dominates the higher energy state. And so as a result, we could get angular anisotropy due to local phase coherence among neighboring excited state nuclei. The 14.4 kV signals don't seem to give us angular anisotropy, and I think that's because the excitation transfer is happening so fast that it's dominated by non-resonant excitation transfer. So we get it moves and moves and moves and moves a zillion times to be able to move macroscopic distances. So now that we have some experimental results, let's go to theory, so we can get theory to connect with experiment. I mean, the whole reason anybody does experiments is in order to verify theory, right? Why do you want to do an experiment?
No, the purpose is to come up with new things for you to vary in your backyard.
So we have a model, we have phonons, we have nuclear energy levels, we have the boost coupling, and the phonon, or the momentum operators connected to creation and destruction of a phonon. The A operator is electric dipole symmetry. So for E1 electric dipole transitions, this would be simplest. Turns out cobalt 57, the 14.4, and the higher energy transitions are M1. They're magnetic dipole transitions. So you need two E1s to make an M1, so the theory is much more complicated for M1. Okay, so I took the theory, plugged it in, turned the crank, and that's the answer. Take notes, you're going to be tested on this at the end. Do the same thing for M2. And this is the answer for one of the cases. And I look at the answers and I think, fantastic, I've exercised the model, I've got expressions, I compare theory against experiment, and they're off by orders of magnitude. Why does it need to experiment? Okay, so we take this model out to the backyard and we make room for it. So before, I had this problem before when I tried to do up conversion, down conversion. So before around 2002, my very first models that could show up conversion, down conversion had an asymmetric loss added. So I said, let me add loss. It worked before, it'll work this time. So I added loss, plugged in, turned the crank, get a prediction for the E1 case, plug in. The result for M1 doesn't fit on a view graph, so I've left it out, so you're not going to be tested on that. Anyway, so I get my answer, the results are orders of magnitude larger, I'm happy, I plug in numbers in my calculator, I find them still off, and I scrunch up the paper and throw it at the garbage can. I practice speaking French. Anyway, the predicted effect in this case is still much smaller than observation.
But was it larger than before?
Much larger. Orders of magnitude larger.
So the loss for the dissipative term is helping.
The dissipative term helps dramatically. In fact, it's not just that, but terms, there's details in the terms that qualitatively match the experiment. I get one effect, which is a short range kind of effect that would be relevant to the high energy stuff. I get this delocalization effect that would be relevant for the 14.4. So it's actually starting to behave qualitatively very much like what I was hoping for. So I'm very much encouraged, but I have to continue practicing French in order for this to work. Okay, so now when I was writing up my paper last year, I was bemoaning about how unfair Mother Nature is, and how nothing works, and it's impossible to get a theory to match any of these wretched experiments. Then it occurred to me that if the basis states shifted off of resonance, it might actually do what it is we need done. And I considered that kind of thing years and years and years ago, but I thought, well, it's probably going to be a small effect, so why bother? So the idea is like this. So here's my excitation transfer. My off-resonant state going up and my off-resonant state going down. In these models, they're perfectly balanced. The excitation energy that you get by a down transition is exactly the same going with the up transition. And having that happen, having these be perfectly balanced, means that the contribution going up this way, the contribution going down this way, they cancel out because you get a sign negative one way, positive the other way, and they kill each other off to precision. So if this state could move, so they're no longer killing each other off, I go thunk, like that. Isn't that cool? Your theory is much better. Then now, because it's not symmetric anymore, you've got a chance of killing off the cancellation. And if you can kill off the cancellation that way, well, a win is a win is a win. So I proposed this, and I thought, okay, fantastic idea. Got to roll up my sleeves and start calculating. So the question is, why would you expect the energies to shift off of resonance? Anyway, it's subtle. Nuclear force is understood as a pion exchange, at least by some people. And the pion, when it's off of resonance, it happened to notice it's off of resonance. And so if the state is off of resonance, if you take a nucleus and if you put it off of resonance, you push it off of resonance, the pion exchange notices that the nuclear potential is going to change. And you can flip through the literature, and there's papers written about this. There's some papers in the late 60s and 70s where people are calculating binding energies of tritons and things like that off of resonance. You can find discussion, people making the nuclear potential, saying a test of the potential, so whether it's that good as to how it changes off of resonance. So here's the E1 transition off of resonance. There's the M1 transition off of resonance, and all I got to do, and to be honest, these expressions look very, very good. So if the bring energy, big quantity, small quantity, and so forth, that will be solved, completely solved, if we can get this to work. So this is really a big deal. So what I want to do now is I'm going to take the deuteron, and I'm going to move it off of resonance. So there's lots of models for the deuteron available. It's one of the best studied system. I've even calculated myself before. So what I want to do is I want to calculate basically the change in the single pion exchange contribution. And the folks who are the physicists will say, well, you're not going to get away with a single pion exchange. You've got to do two pion exchange. You've got to use chiral effective perturbation theory. And I said, well, one step at a time. The long range thing will come from single pion exchange. So I'm going to add the increment to the existing deuteron model and see what happens. So here's the pion. Here's one model for a single pion exchange off of resonance. And instead of getting a Yukawa potential, I get a transmogrified Yukawa potential. And it turns out numerically I could just fit it to a lot of Yukawa potentials. And so I put together a little code that can do this to a few parts per, or actually better than 1 part per million for all of the off-resonant energies I work with. So now let's take, I'm going to hear the groans, but let me take the oldie but goodie Hamada Johnson potential from the early 1960s. So here's the kinetic energy for the deuteron using reduced mass. Here's the 4 terms from the Hamada Johnson potential for the nuclear potential. And I'm getting out now the incremental central and tensor potential correction for the 1 pion exchange term. So I can do this. I mean, basically, anyone could do this. This is not a difficult calculation. And here's what happens. I'm listening for the oohs and the ahs. So on resonance, there's no shift. As I go off resonance, when I have more energy available, the binding gets to be stronger. If you're going off resonance in the direction of supplying, having there be more energy available, the nuclear potential gets very much stronger. And if you go in the other direction, having less energy be available, then the nuclear potential gets much weaker. And at some point, the deuteron ends up not being bound anymore. Anyway, I will point out that this is an MEV, not EV, it's MEV. That this shift in the binding energy is gigantic. So this is a respectable calculation for the binding energy shift off of resonance for the deuteron. Anyway, I think this is a big result. It looks to me like it means that the theory is going to connect now with experiment for excitation transfer. I think this basically solves the problem, how you have convert and down convert. And I think it basically makes all the models.
We need to talk afterwards. We did some experiments using aerosol and photons. We've seen that boosting.
Cool.
I'll talk to you about that.
Okay, let me keep on going. So they had this model together. Let me try the dineutron. And initially this was a mathematical exercise. It was just curious. The dineutron, people have been talking about the dineutron since basically the 1940s. And the nuclear models basically say the dineutron is not bound. And so calculation after calculation, every once in a while somebody pops up and says, my model is bound, and then everybody else beats up on them. And then people go in the lab and they do experiments. And there was an experiment done, and I'm going to blank out on the author's name, but it was published in 2017. And what they did is they took a deuteron that came in with a gamma, just a little bit above resonance, and they were able to select out the singlet S naught. Sorry, not the deuteron. They took something that had two spare neutrons, and they excited the two spare neutrons and got it out in the singlet state. And they were able to measure exactly, what the binding energy was, and they found it was unbound by about 56 keV. So, and people have calculated scattering lengths, and it's definitely not bound. Okay, so the question is, can we move it off of resonance to stabilize it? So here's these are scattering lengths. This is amount of energy off of resonance. Talk about photon-mediated excitation transfer. So this idea is proposed by me in the 1990s and calculated out and shown not to work for the first view of it. Whittam and Larson popularized it a few years ago. In Greccio, I talked about resonant neutron transfer due to phonon exchange and transferring energy, which mathematically is beautiful at a very high rate, but it's probably not going to happen very often due to technical reasons. So for this presentation, I was thinking, what about off-resonant neutron transfer? This would be really interesting. So the basic idea is that phonon exchange, you transfer to a Bragg neutron state in order to delocalize. Another phonon transfer, phonon exchange to come back down at another site. You can move a neutron from one place to another. So the resonant version would look like this. If you could exchange a phonon and also exchange energy with it, you could be resonant, you could go over here and come back down the same way. This is the mathematically ideal, but totally practical way to do it. If these, the non-resonant, off-resonant cases, you have phonon exchange coupled with Bragg states, but to get a neutron off, you need this much energy. On the other hand, if you're doing it off-resonant virtual excitation kind of thing, it doesn't have to be on resonance. So then if you make it over here, then you can come back down. Now this nucleus and this nucleus are sort of, the same. If this starts out being iron 57, this is iron 56, then you can get a neutron to go here, here, come back down, and you move the iron 57 from one place to another place, which would be really interesting. It'd be really hard to detect that you've actually done that, but it's very interesting. Now, much more interesting is if this is one nucleus and this is another nucleus, then maybe you make a new isotope of another nucleus. Maybe you can use neutron activation analysis to see if you've actually done that. That's also very hard. Those experiments will be very expensive because every time you want a neutron activation analysis, somebody's going to want to check into them for a lot of money. So it looks good as a mechanism. We'd like candidates to minimize, to make this work the best, you'd actually like for this state to be as close to this one if they're not the same. So if you're going to go from one nucleus to one element to another element, you'd actually like to look through the tables and balance this energy so that you can be close to resonance as possible. So I downloaded an isotopic mass table. I put together computer code I write in 17th century Fortran. My documentation's in the original Latin. So I had my code spit out nuclear pairs with the unstable nucleus, and I said, let's order it by the energy difference. So here's what came out. Hafnium, if hafnium-179 gives up the neutron, you get hafnium-178. If argon-40 gets the neutron, it turns into unstable argon-41. The energy mismatch is 40 volts, 43 volts. And that's the lowest of all the combinations in the table. There are others as well. And so, in principle, these are candidates. So for the argon one, for example, you can imagine taking an argon beam, having it go into a hafnium target. And that makes lots of terrorist phonons. And if the hafnium's Riesling crystalline and the argon goes in, then you have the possibility of transferring a neutron to argon and seeing radioactive argon. And that you have a possibility of detecting. Anyway, here's the overall reaction. Conclusions. Anyway, conclusions. I've been interested in excitation transfer models and so forth. I have a theory for it. The theory had headaches because I didn't agree with the experiment. I think maybe it's debugged now. The off-resonant binding energy shift looks like it's going to make that work. It's going to look like it's going to solve most of the outstanding problems that we have with the models. It's going to allow me to connect models with experiment. We have a new proposal for a single neutron transfer reaction, which is testable, and I would like to move in the direction of actually putting together some experimental tests to see if we can see the effect. And then a proposal for this off-resonant multi-neutron cluster exchange in connection with Ira Moore's experiment. Thank you. No questions? Okay. That's interesting.
Peter,
Yes, first.
my question is, have you tried to calculate just the transition rates using golden time rules? Because it's very easy, plus perturbation theory, quantum perturbation theory, and what is important to know what is the overlapping wave function in this matrix.